Voltage alone does not determine how much current flows throughout a circuit. The materials used to conduct electricity have properties that prohibit the perfect flow of charge in a circuit. This is called resistance. As you can see on the screen, the slowing or the prohibiting of electron flow. Resistance is a measurement of how strongly an object will oppose current. This depends on several factors. The first being resistivity. Every material will have its own resistivity value. Some materials are better conductors than others. Resistance and resistivity are two different things. It also depends on length. The longer objects are more difficult to pass current through. Everybody wants a long iPhone charger so that they can lay in their bed and have their charge continue to flow to their phone. Well, if you have a very long iPhone charger, it's going to take a longer time to charge than a regular, smaller iPhone charger. Resistance also depends on the cross-sectional area of a wire. Wider objects allow current to pass more easily. Think about being in the hallway and having a lot of students in the hallway when you want to pass versus in between periods, or not in between periods, but during a class period when you want to use the restroom. It's a lot easier to travel to the restroom during the period than it is during the bell. The last is temperature. If the object is warm, the molecules inside will be bouncing around more, opposing current. For resistance, we have an equation. R, capital R is resistance, equals rho, which is resistivity, L for our length, and capital A for our area. We are always talking about the area of a circle. So area of our circle, pi r squared. The unit for resistance is the ohm. It does look like that, the symbol, the Greek symbol, omega, capital omega. Resistance in wires, we want to have wires that are the best conductors. It allows for the most current to flow from one place to another. An ideal conductor has minimum resistance, which means that it is going to be a short conductor. Shorter conductors have low resistance. We also want an ideal conductor to be wide. Wider conductors have a lower resistance. And lastly, we want an ideal conductor to be cold. Cold conductors have lower resistance. Ideal conductors, remember these three things, are short, wide, and cold. Short, wide, and cold allow for ideal resistance. So, we want to first calculate the electrical resistance provided by a piece of copper wire with a length of 1 meter and a cross-sectional area of 0.01 meters squared. Do not forget, meters squared is area. So here's our formula. We go through and we plug it in. On page 4 in your reference table, you will find your resistivity chart. That is where you're going to find your rho values. So this 1.72 times 10 to the negative 8 ohm meters comes right from your reference table. Copper, that is the resistivity value. Taking all of this, plugging it into your calculator, you do end up with 1.72 times 10 to the negative 6 ohms. Make sure you try this in your calculator. What is the composition of a wire with a resistance of 31.8 ohms if it is 5 times 10 to the 7 meters long and has a cross-sectional area of 0.025 meters squared? Well, here we're looking for composition, so we're looking for what kind of material it is. Again, our formula, we have 31.8 ohms equals rho, which is what we were solving for, times our length divided by our meters squared. The unit is squared. The number is not. Be careful. When in doubt, put it over 1, 31.8 over 1. We cross multiply, solve, and we end up with 1.59 times 10 to the negative 8 ohm meters. That is the unit for resistivity. If you look on your resistance chart, you will see that this matches silver.